Hi all, welcome back. So today we are going to understand the ADCS. This is lecture 2 and lecture 1 just briefly understand the ADCS and what's the importance of the ADCS in spacecraft and what's the fundamentals over there, how we can understand this. So yeah, so this lecture 2 and I'm just uh, trying to understand this ADCS and what's uh, parameters and what's the theory uh, is needed for to understand that. So I'm trying to explore this theory and with the examples, trying to simplify the theory and trying to understand the trying to interpret this theory in real application. So that's our main objective to be the way to understand the EDCS. Hope you understood. Yeah. So since we know that ADCS, name itself tells us attitude determination and control system, right? So basically, this tells about the orientation. So since in our in the space, we want to orientation. So we understand that attitude tells about the rotation orientation of the spacecraft, and what's the why we needed to control the attitude. So we pointed out, we outlined some set of applications why we needed. Yeah. So from today, we just try to understand that before uh, before understanding the attitude determination and control, first we understand that frames. So there are some set of coordinates and reference frame to be understood to for understanding better for attitude determination control system. All right. So here physical interpretation we want what is a physical understanding to our real ADCS implementation. So yeah, so space guidance. So generally guidance navigation control. Generally I call to NGC. First we go navigation where we are, then go for guidance where we want to go, and then we want to perform, give the actuated target to achieve that, right? So that's the way we have to go. Okay, so most of the generally people they GNC they call. Okay, all right. So what we'll learn in this actually. So why reference frame are necessary, right? And physical vectors versus coordinates, inertial reference concept, earth center inertial ECI, earth center, earth fixed. This is also very important. And local vertical, local horizontal, short form is called LVLH, and spacecraft body frame and sensor and actuator frames and frame transformations, direction cosine matrix DCM, practical ADCS frame chains, and common implementation mistakes. Sometimes you know we commit mistakes also to implement. So we need to also understand where is likely to commit mistake. All right. So here basically every frame we need to ask what we want to achieve and why is needed and how we have to uh, I mean how we can um, uh, set a frame, basically, you know assign a frame, I would say, and where it is going to be used, right? So there's a some set of question to be asked to understand the frames. All right. Okay. So important acronyms like ADCS, this is a like attitude determination control system. Already we know. So this is a short form we know should know understand that. ECI or center inertial frame, and ECEF or center or fixed. LVLH local vertical local horizontal. DCM direction cosine matrix. IMU inertial measurement unit. CMG control moment gyroscope. And SO3, this is like a special orthogonal group in 3 dimension where we present the our attitude. We will discuss in details. One is a SO3 and one is a AC. We will explain this all this stuff. Yeah. So why this meter frame acronyms are not just naming conventions. Each one represents a different physical reference used by navigation and estimation, guidance and control, right? So there are various frame involved in the NC implementation. So we need to understand thoroughly so that distinction uh, can be established. So could be established to understand the navigation or basically estimation and guidance and control. All right. So first fundamental question like spacecraft is pointing up, right? So is the statement complete? Answer is no. We must specify up related to which reference frame. Reference is important. Okay, so then only we could understand that. Yeah, which reference you talking about. So, so physical interpretation up can mean different directions, right? If you present a DCI or center inertial or center earth fixed, local vertical, local horizontal, body sensor payload coordinates. They are set of frames to be assigned, to be specified, then only space is pointing up or down with respect to this frame. All right, because if space was up in one frame is not is maybe not up for other frame also, right? So that's a very important to specify the frames to understand the spacecraft directions, spacecraft orientation basically. So do you need reference frame? So the quantities like position, velocity, direction and attitude. Attitude deals with the orientation, right? So must be discussed related to some reference. So reference is important, then would know where position there, where attitude, how much orientation subtended by spacecraft, right? So example, spacecraft may need to point like antenna toward Earth for communication, solar array toward Sun for power, like charging the battery, camera toward the target, right? To like in RP or Indigo proximity operation, we require camera to like yeah, so that time so that it should approach, right? So docking exit toward another spacecraft. So engineering significance without a common frame, sensor data cannot be compared. So that's a very important. Like you have the sensor suit, right? And you have to perform the sensor fusion. We will discuss later in the details about the sensor fusion. So right now you understand that we have set up data recorded achieved by multiple sensors, but we need to fuse this data to get to make a decision, right? So for this we should be having same frame, then only we can compare it. Otherwise comparison could not be established. This is wrong. If you go for we have the sensor measurement, the different frames, we cannot compare directly. So guidance reference become ambiguous. So that's a very important. Guidance reference become ambiguous, with no clarity. Control errors may be incorrect. So without a common frame, so all should be in common frame, right? But implementation is not a common frame. So actuator commands may point in the wrong direction, because in the end we want to control the predefined attitude, but it is not there. So what will do? So we should, that's a necessity, urgency of common frame. So you will able to make it common frame once we understand the all frames to be required for various purpose, various subsystem to be implemented, right? Yeah. So reference frame, I just try to draw it. So reference frame consists of the, so this is very important. Reference frame is consists of the origin and 3 orthogonal axes, right? So this is very important. So it should have the consist of one origin, and is also has the 3 orthogonal axes 90 degree apart. It should subtend 90 degree, right? So then only we can say this is a reference frame. So reference frame and coordinate system. So there's a very sometime confusion over there. We need to understand that here. So reference frame define a physical difference. They define a physical difference, like it consists of the origin, orientation, and motion of axis. All right. And coordinates are numerical components used to represent a vector in that frame. Okay. So that's a importance difference is there. We need to understand that reference frame and coordinates. Yeah. So important because here then only we will able to measure the value. So this value vector we call the like coordinates, right? But reference frame defines the physical reference, whether it is a position or velocity, acceleration, orientation, right? All right. But to measure this quantities, we should have the reference frame, which consists of the one origin plus 3 perpendicular orthogonal axes. All right. Hope you understood. So important, the physical reference and its numerical coordinate representation are related. Physical reference and its numerical coordinate representation are related, but they are not the same concept. I think we will understand in detail later once we proceed this course. Uh, yeah. So right now you just understand simply like this is physical quantity which want to measure. So what are numerical components is called the coordinates, right? So these are related but not like same concept. Okay. So physical vector and coordinate representation. Suppose physical vector B exists in a space, its component frame A. So B in a frame reference frame A, we have the, let us say we have the velocity component. So we are presenting like that. So this is a B to present, this is a x-axis and this is a like saying about the frame, right, A frame. So while in a frame B, this is a frame B. So this is a way to we can present it, because there are various of not only one frame. So we need to assign, we also tells about the frame, which frame you talk about is quantity. So interpretation, the physical arrow in a space is the same right? And only the numbers used to describe that arrow change. Okay. So concept check, did your vector rotate? The numerical components of vector range from A B to B B. Okay, B1 to, let us say, B to here, and you come back this one. So we need to see that what's the values there, this one, right? So the physical vector necessarily rotate? No, this can simply represent the same physical vector viewed from a different coordinate frame, right? So point is that, let us say the same, this is one point, right, and we are saying this reference frame here. Okay, this is frame, different frame A, this frame B. So it's not essentially like essentially is rotated, right? It has a different coordinate frame for this different components vector, and for this different component vector, right? All right. So point is that frame should be same, then only we should get to know, okay, this is rotating or this is stationary, right? So this can simply represent a physical vector viewed from a different coordinate frame. So changing coordinates is not physical rotation. So that's very important. We should understand that here. Changing coordinates, not a physical rotation. We are changing coordinates sake of our simplicity, our understanding, right? We want to understand the subsystem involved in this ADCS, right? And most of the components mean subsystem, of course it should have this different frame, right? So changing the coordinate, it doesn't mean that a physical rotation over there. So major frame used in Spacecraft ADCS, first is a Earth center inertial, okay. Then Earth center earth fix is also be used, and Earth center inertial, some we use the local vertical, local horizontal, okay. Then we use spacecraft body frame, okay. Then also we use the sensor frame and actuator frame. All right. So these are the ECI, ECF, EF, and local vertical, local horizontal, and spacecraft body frame, and sensor frame, and actuator frame. So system level view, like a real spacecraft ADCS continuously converts information between these different representations. So that's a very important, like to take a further decision, how internally computation to be needed, and internal this computation gets corrected and decision to be taken accordingly once all transformation to be taken place correctly, right, in all different frames over there. Okay, so hope you understood the importance of the frames. Yeah, now we move on the classification of frames. Yeah, so first is a inertial reference frame. So inertial reference is a reference in which Newton's law can be applied without adding fictitious forces caused by the rotating coordinate frame. So it is stationary basically, right? So it means whatever is like without I mean, what we can say, like without considering the causing force, whether it is stationary, so it is stationary, and rotating, so it is rotating, right? Yeah, in motion, then motion, right? So that's important. So theoretical significant Newtonian dynamics, we will understand this also. Angular moment concept, orbit propagation, attitude kinematics. So orbit propagation, rise and up and down, we want to Understand this also. So ADCS significance. Inertial attitude reference are useful for start pointing, deep space observations, inertial sluice, and attitude propagation. Alright. So inertial frame is a reference in which Newton's law can be applied without adding imaginary forces caused by a rotating coordinate frame. Some effect will be there for rotating coordinate frame, but we will discuss what they mean actually. Understood? Yeah. So second one is a earth center inertial frame. So ECI. So earth center inertial. So origin is approximately at the earth center. We consider here center is a earth center. Oh, sorry, origin considered as a earth center. And axes are tied to an inertial celestial reference. Okay. So earth rotate related to these axes. So that's a very important. So so it means once earth rotates, so because this is a pointing on the earth rotate, this frame also rotate, right? So with respect to earth is stationary. So earth center inertial frame. So axis tied to the inertial celestial reference. Earth rotate related to these axes. Okay. So that's a very important. Earth is rotating with respect to these axes. This is stationary. Earth is rotating, right? And why ECI important? Because orbital mechanics we will understand in upcoming course lecture, like orbital mechanics and inertial attitude dynamics. We need a reference that is not rotating with Earth's surface. Typically use spacecraft position propagation, orbit state vector, inertial star directions, and inertial attitude references. So implementation, like let us say navigation filter may store, we want to store, so LAR, sorry LR and LB. So while ADCS estimator simultaneously computes space orientation related to the inertial frame. So we want such frame which should not be rotated with the Earth surface. Okay. So EC is not a one unique frame. Important because term ECI describe a family of Earth center inertial reference frame. It is not uniquely specific for one realization. Example may differ in the reference epoch. We will discuss what is the epoch actually, and celestial reference realization, treatment of precision and notation, transformation accuracy requirements, engineering interpretation in software and interfaces. Never write only ECI if mission accuracy requires a specific celestial frame definition. Okay. So Earth center, Earth fixed frame. Now we move on the another one. So generally approximately at Earth center, axis rotate with Earth. So this is a important. ECI is not fixed with respect to Earth as rotating, but this is a Earth center, Earth fixed. So axis rotate with Earth. So this frame is moving with respect to the once Earth is moving, right? Yeah. So Earth fixed location remain approximately fixed in coordinates. So that's a very important. So physical interpretation, like imagine painting the coordinates actually directly on the earth. Sorry, pointing, should be pointing, yeah, type or okay. So earth rotates, actually rotate with it also. I think it's a correct. So why ECEF important? Because where used, like let us say for ground stations, we need it, and latitude longitude conversion, earth fixed targets, navigation, communication geometry, and real implementation we are going to use. Suppose a imaging spacecraft must observe a known location on earth. So target coordinates may first be known in a earth fixed frame. They are then transferred to the frame required to by guidance and ADCS. So these are the necessary important importance of the ECCS importance, right? So ECI versus ECF, let us say understand. So full form is center inertial and earth center earth fixed, origin earth center, this also origin center, okay. Axis inertial, like rotate with earth, this is a fixed, and ground station moves here, ground station moves here, nearly fixed. So this is very important where you are seeing actually, right? So basically in spacecraft is showing like a fixed, but in case of ECI is showing moves, right? So orbital dynamics, natural and less natural. So generally orbital dynamics we understand use the ECI, and earth target time bearing and natural. This is time bearing, but here natural. So interpretation ECI and ECEF describe the same physical world from a different reference viewpoints. Where we gonna to see this. Yeah. So ECI to ECF transformation model, meaning if a vector has inertial coordinates like this one, so earth fixed coordinate can be written as, this is be going to change in the ECEF. So this is a direction Cosine matrix, we will discuss later, and from ECI coordinates to ECEF, so that we can like I told you now, like we want to transformation to be required, right? We have various set of frames, so kind of frames, so we need to transform, right? Same frame, then only comparison to be taken place. Yeah. So vector, what is the interpretation we can point here? So vector did not move physically, this is very important. Observe a change from inertial frame to earth fixed frame, okay. So these are the things, I mean points to be understand here. Yeah. So why do we need a orbital frame? Now we move on one more frame, orbital frame. So this is important in terms of the spacecraft perspective. So suppose spacecraft must maintain the nodal point, lowest point, I would say, zenith point also there, top, along track pointing, cross track orientation, local orbital alignment. So why not use ECI directly? We can, but these requirements are naturally tied to the spacecraft local orbital geometry. Okay, so that's why we go for orbital frame. So therefore, orbital frame simplifies guidance and control interpretation. Okay, so this is a very important point. We will use the ECI also, but point is that naturally we link to the local orbital, right? Yeah. So local vertical, local horizontal. So this is a very important. So local vertical, local horizontal frame is a local orbital frame constructed from spacecraft position and orbital geometry, right? So this is constructed from the spacecraft position and orbital geometry. Okay. So this is also one frame, is called the local orbital frame. So this is constructed from the spacecraft position and orbital geometry. All right. And physical meaning, local vertical is related to the radial direction, and local horizontal lies in the plane perpendicular to the local vertical. We will explain in detail these things. So the frame moves and rotates with the spacecraft orbit. Once spacecraft orbit is rotating, so the frame moves also and rotate also as well. So important, local vertical, local horizontal convention not universal, always defines axis directions properly, clearly. Okay. So orbital geometry behind local vertical, local horizontal. Spacecraft inertial position, let us say R. Spacecraft inertial velocity, let us say B. So orbital angular momentum H equal to R cross B, right? So this is velocity, this is R. So we can find out the angular momentum, this one, and radial in any direction we can find out the R. Okay. And orbital normal direction, this one, perpendicular for this. Okay. And then constructing one orbital frame convention. One possible orthonormal orbital triad is this one. This is a position we can say, and this is our angular, and again cross we can get the, this is a perpendicular, so this is a further is a our next remaining axis, yeah, coordinates, right? So engineering rule, never assume another team's local vertical local convention. Exchange origin plus exit definitions plus signs and transformation directions. Okay. So radial, along track and cross track, what is the important value? I mean, what is the terminology important here? So I'm just trying to understand. So radial means approximately along R, a center to space center, and along track, this is approximately tangent to the orbital path and related to the local spacecraft motion, and cross track normal to the orbital plane related to the, this one already we seen, right? Angular momentum. So practical use, these directions are badly used for proximity operations and formation flying, earth observations, and rendezvous guidance. We will understand this, what is a rendezvous proximity. Okay, don't worry, just try to be just building up the foundation. So critical concept, local vertical, local horizontal rotates. So question, if a spacecraft remains perfectly earth pointing, its attitude constant relative to inertial space? No, right? Because orbital frame rotates as the spacecraft travels around Earth. So orbital frame rotates once spacecraft travels around the Earth, right? Therefore, the spacecraft must also continuously rotate related to the inertial space to remain aligned with the local vertical, local horizontal. So this is very important. Zero local vertical, zero horizontal attitude error. It does not mean that it not signifies that the velocity in the inertial is 0. Okay, means it's not, it's inferior, right? Okay, so orbital angular rate for ideal circular orbit n is equal to under root mu by r3 rq. Mu planetary gravitational parameter we will discuss, and r is orbital radius. So ADCS significance in order to point spacecraft may have attitude error equal to 0, but it still require a non-zero reference body angular rate, right? Okay, so spacecraft body frame is fixed to the result spacecraft structure. So this is your body frame, and axis may align with the structural axis, payload both side, principal inertial axis, docking axis, and physical meaning. If the spacecraft rotates, the body frame also rotates with it. This is a body frame. So therefore, attitude can be viewed as the orientation of body frame related to the chosen reference frame. So this is very important. So basically, if a body frame rotation we can see with respect to the assigned reference frame, then this is called the our spacecraft spacecraft attitude, right? Because this frame is always going to fix on the spacecraft body, right? So attitude equal to relative orientation between frames. So this is very important, which frame you want to assign. So orientation between frames, right? Inertial attitude, for inertial attitude is FB related to the FI. This is body frame, right? Related to the FI. And orbital, for orbital relative pointing, so this is body frame attitude related to the local vertical, local horizontal. For a payload, so FP related to the body frame, because payload we are defining with respect to the body frame itself. Yeah, further if you want you can again transform to this here again, this is not a problem. So key interpretation here, there is no meaningful absolute orientation without defining the reference against the which the body orientation is measured. So this is very important, which you have to fix the frame. All right. So sensor frames, sensors often have their own coordinates frames, right? Like example we are illustrating like star tracker, sun sensor, inertial measurement unit, magnetometer, navigation camera. So measurement may arrive as SB. So ADCS may need to the same vector in a body coordinates, right? So this is sensor frame, and this is body frame, right? So we have to transform again. So one matrix to be required, right? So those are there. We need to understand of various. Yeah. So why sensors of body calibration matters? So theoretical point of view, the estimator assumes a no rotation between the sensor axis and body axis. This we know, right? So real implement, suppose a star tracker is installed with the mounting error of the 0.2 degree. So even if the sensor itself is extremely accurate, the spacecraft level attitude solution can inherit this systematic misalignment unless calibration is performed. So this is very important. We already know how much rotation is there with respect to the sensor axis and body axis. So be always to be corrected. So that's the calibration to be needed. So even though sensor itself has more accurate, but still this systematic misalignment to be corrected. So that's why calibration is performed. So what we understand from here, sensor accuracy and mounting knowledge are two different error sources. This is very important. Sometimes people confuse sensor accuracy and mounting knowledge are the two different error sources. Okay, sensor accuracy and mounting knowledge are the two different error sources. We need to understand this one. We will repeat again. This is very important point, sensor accuracy and mounting knowledge, where we are mounting these sensors. All right. So suppose sensor frame alignment, practical related try to understand. Suppose your camera optical axis is on the z axis, z plane direction, and but the space for docking axis is xp. So then a controller cannot directly treat camera coordinates as the body coordinates. You understand this way, docking axis don't need not to explore that much here. We are just trying to approach the let us say our spacecraft should be intended to this axis, xp direction. Okay, but camera is there, so camera to be oriented towards this one actually. So then a controller cannot directly treat camera coordinates as a body coordinates, right? Instead, you applied first this one. This is your spacecraft. This is the body. So we have to transform. So must be applied. So implementation risk here. If CBS is omitted or reverse, so correct visual estimate can produce an incorrect body frame command. So this is very important once if you miss the any frame parameters. So actuator also have physical directions, like for example action wheel spin axis, magneto coil axis, thruster force vectors, control movement gyro scope axis. So for multiple actuators, tau is equal to A into U. So A is a actuator geometry, a allocation matrix, where we are let us say we have the where we are mounting lot of the, so we have to put one matrix to be there, right? So use individual actuator commands. So based on the actuator command, this is I think based on the our actuator geometry, this is always going to fix, right? So based on the individual actuator command, let's change the our net output. So why actuator geometry matter? Because if controller requests this one, right, like torque toward axis, by axis in z direction, so can every actuator directly generate all three components? No, we have to specify, right? So each actuator produces force, dipole, momentum exchanges along its physical axis x by z. So therefore control allocation maps desired body torque to individual actuator commands. So desired body torque to the individual actuator commands. All right. So same vector in two frames. For a physical vector expressed in inertial and body coordinates, right? Same physical vector expressed in inertial and body coordinates. So you may write this like that. I am telling to you. So you just convert to direction Cosine Matrix, will get the body frame, and conversely you also similarly you can explain this also, this one. This you convert here, again you convert it, then again you will get the different frame, right? So same vector in two frames. So proper orthogonal DCM, you will get the same actually, this one and this one. CBI is equal to the CBI transpose. So this is basically same, right? So direction Cosine matrix. So direction, this is now we just move on to various rotations, how we can how we can represent the rotations. So first fundamental, we just go for direction Cosine matrix. This is a 3 by 3 orthogonal rotation matrix. They'll represent the C belongs to the SO3. 3 stand for the 3 axis, right? So where 3 SO3 is a special orthogonal group in 3D dimensions. The properties to be understood there. So this matrix, so this should be identity matrix, right? If you put this C transpose C, so basically this is orthogonal matrix, right? For which determinant for orthogonal matrix generally should be plus minus 1, but sake of a right hand thumb we are considering, so that's a putting here plus 1. We have to consider the plus 1. So what does DCM mean physically? Suppose BB is equal to CBI and B, so each row or column of matrix contain the information about the relative orientation of two frames. Just you have to understand this way, 3 by 3, whatever row and columns there, this is only telling about the relative information of the orientation of the two frames, that's all. Body frame, space का body frame, best fit would be any inertial frame where you have to consider a frame, right? Reference frame. Yeah, so interpretation, DCM is not simply a matrix, it encodes the how the axis of one frame are oriented related to another, right? This is very important. So why DCM inverse equal to transpose? Because basis vector of orthogonal frame satisfy this rule, right? So that's why it's called the inverse equal to transpose. So this is orthogonal matrix rule also there, right? Okay. So physical meaning that going from A to B, then from B to back to A must recover the original coordinates, right? That's a very important. That's the mean actually. If you go from this to this frame and same you go from this to this, it should be achieve the same frame. It's not be go for different frame. That's an important here. All right. So passive and active rotation. Passive transformation means that physical vector remains fixed, right? Only coordinate system changes. That's called the passive transformation. For sake of our simplification, our analysis, we just change the frames, coordinate frames, right? But physical vector is not fixed, is not changing, right? But where active rotation means that coordinate frame stays fixed, but physical vector rigid body rotates. Then we call the active rotation. So this is a terminology we have to understand here, because there are a lot of frames, there are various parameters to be considered for various frames, right? So significant that many transposons and errors are an attitude software arise from mixing these two interpretation. So this is very important. We have to take care to understand that. We will try to repeat these those things as much as possible in our coming lectures. So we will get more familiarity soon, right? So real ADCS data flow, how we can get guidance reference, then go for sensor measurement and frame transmission, attitude estimator, then attitude controller. I just row I would say actually, and it's not like complete corrector based on the guidance reference. So first I think sensor measurement should be there, then guidance loop I am not making here. So implementation significance, frame conversion is not a separate academic exercise. This is embedded throughout the actual ADCS software pipeline. So once we build the flight control software for ADCS, so all frame conversion and transformation is needed. We have to then we have to do, then only we get, it should be part of this deployment. So for example, set tracker to attitude estimator, generally used for set tracker for attitude estimator. So star tracker measures means, let us say this measure yes is transformed to body frame. So we are just transforming this body because this is sensor frame, right? This is sensor frame means own star tracker frame. So we are transforming to body frame with multiply the direction Cosine matrix known as a inertial star direction. Okay. So the estimator compares corresponding inertial and body frame observations to infer space attitude. So catalog is given to the sensor, given to body frame, then given the accurate estimate. So okay. So that's a very important. We have to measure, we have to compare this accurate estimate data. Okay. So example nodal point spacecraft. So guidance may define desired altitude related to the local vertical, local horizontal. Okay. And estimator may provide actual altitude related to the ECI. Okay. And therefore controller may require ECI to convert to local vertical, local horizontal, then body frame, right? So that's a conversion to be needed. Transformation before computing the final attitude error. So engineering perspective, controller can be mathematical correct, but still fails if the input states are expressed in inconsistent frames. So very important frame to be saved. Then we have to, because if you measure the one quantity here different frame and you design the controller for different frame quantity, how it is going to be correct? Yeah, second is like visual navigation, like camera docking. It's like we are just one spacecraft heading to another spacecraft and mating each other. That's a docking to avoid it. Like this is a mechanical way to do that. So, for this random proximity operation to be required, yeah. So navigation camera may estimate the target position as CPT, and spacecraft controller may require target error in body coordinates. So navigation camera may estimate a target position as this one, means camera frame, but spacecraft controller may require target error in body coordinates. Then we have to go for the body coordinates from camera frame to body frame. So practical meaning is to that here, camera geometry and control geometry must be connected through a non-camera to body calibration. All right. Yeah. So frame transformation in software, practical implementation should explicitly track like source frame and destination frame, time stamp, units, axis convention, rotation convention, calibration version. This is also important. Something going to change and we should aware about it. So software engineer role like avoid storing an unlabeled vector such as like this is very difficult to understand, where this point is which frame is so far, right? So frame errors can look like controller problems, right? So suppose a controller response moves in a wrong direction. Possible causes include a wrong controller sign, reverse transformation, incorrect sign axis convention, sensor mounting error, degree and radian versus. This is also very important. Sometimes we commit mistake in conversion also, unit conversions. Body and inertial angular rate confusion. So practical diagnostic lesson is here. Before retuning against controller gains, verify a coordinate frames and signs. This is very important. Sometimes our control works fine, but we commit mistake here. So it is very important to take care of this point. Yeah. So frame error can imitate an unstable or incorrectly tuned controller. Okay. Yeah. So common reference frame mistake like mixing ECI and ECEF, assuming all local vertical, local horizontal definition are identical, reversing CAV and CBA, forgetting transpose inverse, yeah, and incorrect sensor mounting matrix, and mixing right-handed and left-handed axis, act in passive rotation confusion, mixing Euler angle rates with angular velocity. We will explain this also, no worries, and missing time stamps during transformations. So always define frame plus axis plus sign plus direction and time stamps and units. So first check question like can space का attribute be defined without specifying reference frame? No. Yeah. So specifying reference frame, then only we can define the space का attitude. So attitude is a relative orientation. Example like body frame related to the inertial frame. Body frame related to the local vertical, local horizontal frame. All right. And concept 2 question like space remains perfectly local vertical, local horizontal aligned. Is the inertial angular velocity 0? No. So local vertical, local horizontal rotates with the orbital motion, right? So one orbital frame there, right? So therefore space must rotate related to the inertial space to the remain to is aligned, right? But not aligned to the inertial angular velocity, right? Because it's not aligned, so inertial angular velocity will be there. Okay. If a coordinate transformation changes the vector components, so has the spacecraft necessarily moved? No. Passive transformation changes only the coordinate representation, one frame coordinates to the second coordinate, but any physical no orientation. So make describe exactly the same physical vector. Why can two correct teams still obtain opposite signs for the local vertical, local horizontal axis? Because different axis convention may be used, right, for the local vertical, local horizontal. Alone does not uniquely specify all signs and axis directions. So everybody, different person, they can plan their way. So always extend to the mathematical axis definitions, not just the frame name. So this is very, very important. And why can a high accuracy sensor still produce an inaccurate spacecraft estimate? Because spacecraft level accuracy also depends upon the mounting alignment, calibration, frame transformation, timing, estimator modeling. So you know, selecting a high accuracy sensor would not ensure that we achieve the attitude correctly. So it means it give the because it also depends on many parameters: mounting, placement, alignment, calibration, frame transformation, timing, estimator modeling. All right. So complete conceptual picture like inertial ECI, then go for earth fixed inertial frame, ECEF, orbital frame, low vertical, low horizontal, spacecraft body, and remaining go for the sensor and actuator. So this is physical world, then reference frame, then coordinates, then transformation, then ADCS decisions to be taken out. So what we understood for this lecture? So the vector is not the same as the coordinates, right? So attitude is relative orientation between the frames. ECI support inertial descriptions. ECEF support earth fixed descriptions. Local vertical, local horizontal supports orbital relative descriptions. And body frame moves with the spacecraft. Sensor and actuator frames require calibrations. Direction Cosine Matrix connect coordinates representations. Local vertical, local horizontal rotates related to inertial space. And frame consistency is critical in the real ADCS software. So same physics, different frames, correct transformations, right? Same physics we have to apply for different frames and correct transformations. And this is our last in lecture 3 we will discuss about these things. Actually we understand that. Hope you get an idea. So that's all for this lecture.